it will be slightly more foundational, so to speak, but it's still about something which involves, let's say, cold atoms, experiments, and things like this. But okay, so let me jump directly into it. It's some work that I've been doing since my PhD in collaboration with some people from essentially Bilbao and Vienna, from the theory part, and some experiments in Hannover in Germany and in Barcelona. So just to give a quick glance of about how the talk will be, I will try to be quite pedagogical, but so essentially I will touch three things. One thing is how to detect entanglement in the lab, based on the experiments in the collective measurements, and then how to quantify entanglement in two different, let's say, slightly different ways. And I will present some results also from experiments. So, but first let me start with the stating what I mean by entanglement and the problem itself. So consider now you have a many-body system or an particle system, and the first thing is that you want to divide your system into parts. Okay, you can think of it as n particles, but you can also divide it into subsystems, let's say. And for the sake of simplicity, let's consider first two subsystems, and then you, mathematically speaking, you divide the system in two parts, and you want to define a state which is given by a tensor product of a state into part A and a state into part B. And when you consider such a state and you mix it with classical probabilities, so numbers from 0 and 1 which sum up to 1, then you define what is called a separable state. And the idea is that you can obtain this by operating separately on these two parts and just with some classical communication between them. And the goal is to detect a state which cannot be decomposed in this form for any possible probability distributions and states of the subsystem. So this is what is called an entangled state. Okay, so that's the problem. You might ask, why do you want to do this? It sounds like a silly problem, maybe. So first of all, it's one way to witness that in experiment you have some genuine quantum effects. I think this is more or less accepted now. And it's also, it has been discovered that it's somehow a necessary prerequisite for many technological applications like quantum simulators or sensor or other things. And also, it has been noted that there is some interesting connection between entanglement and many-body physics. So this is a further motivation maybe to go into the calculation of entanglement measures and verify that these are also present in the experiment in the lab. And I think for me the most important reason is that it's also an interesting mathematical problem which is very challenging, and it's let's say an open question since decades now, and it still attracts a lot of efforts. But anyway, so first thing is to detect whether you have a state which is separable or not. And one should note that I'm focusing on many-body experiments, so not only two spins, but you have many particles, and you cannot really distinguish the state of the individual particles, so you cannot make a full tomography of your state. That's simply impossible. And so you should use the measurements available, so that the quantities available from the measurements, which are very little as compared to the information contained in the state. And but actually there are some methods that work very well, and actually they use the simplest amount of information you can use, which is second-order moments of ensemble measurements, which is what they actually can estimate from the experiments in cold atoms very easily, relatively easily, let's say. Okay, so now what is the idea, let's say, theoretically speaking? So now I'm going to present a way of mathematically distinguish a separable from an entangled state based on these certain observable quantities. And these are variances of operators. So let's consider now the variance defined this way, like connected second moment, of, let's say, two spin directions, Jx and Jy. And we know from Heisenberg uncertainty relation that there must be some non-trivial lower bound here of the sum of these two variances, because these two observables don't have any common eigenstate. And okay, I mean, if there is some such a thing, then you have to calculate what it is. But okay, let's assume you have a non-trivial number there. Now you consider, this is a single particle observable. Now you can consider the collective observable, which is defined like this, like a sum of jxa plus jxb, and the same to y. And then now you consider the variance of such collective observables, and it's actually quite easy to show that twice this bound give you a threshold which must be valid for all separable states. So whenever you are below that threshold, you know that your state cannot be separable, it cannot be decomposed in a separable way, whatever single particle states you might consider. And actually, this is rather, yeah, okay, this is what I say, that lower bound holds for all separable states. Actually, this was noted in several papers. I think here you cannot really read the references, but okay, I can tell you if you want to know this. Actually, I can also present you the proof because it's really straightforward. And the idea is that the collective variances for a product state, they simply split into, first of all, they are concave quantities. So if you mix something with some probabilities, you get a lower bound like this. And now for collective variances, if your state is a product state, they simply split into the sum of two of the local ones. So now if you have a lower bound on this sum and on this sum, you just simply add up and you have, so you can now believe me that such a lower bound will hold for all separable states. And so if you go below this threshold, there is no way your state can be decomposed like this. And that's essentially the idea and what you want to verify in the experiment afterwards. Okay, a similar method, which is somewhat more powerful in practice, it's relying on this other form of the uncertainty relation now. But the reasoning is somewhat similar. You take the collective observables, and here I can show that, I mean, this is a definition, but you can, I mean, play with it a little bit. Here I put a minus sign to get something non-trivial. And so you can show that now this inequality here is also a criterion which is valid for all separable states. So, so this way, by measuring these quantities and like checking this threshold, you can tell whether you had entanglement in the system or not. Or at least you don't know. But if you go below the threshold, you certainly know. And all of this can be now generalized easily to multi-particles, so many body states. And so the reasoning is exactly the same. Now the collective observable is the sum of the individual spins and so on. And now the only difference is that you get n instead of 2 here, as you might very well imagine, I suppose. So all of this, at least for this form of the criterion, straightforwardly generalizes to n particles. And actually the other maybe interesting thing of this is that this kind of criteria are somehow connected with what is called the spin squeezed state, which was introduced in a totally or slightly different context, like only about some metrological applications and in analogy, let's say, with bosonic squeezed states, but it was not connected with entanglement in the very beginning. The idea was that you have a state such that it saturates the Heisenberg uncertainty relations for the spin, and both variances, let's say in x and y direction, have the same value, which saturates the threshold for a fully polarized state. So the state is first of all fully polarized in one direction, let's say z, and then the other orthogonal variances are equal to n over 4 in this case, because let's say for spin half particles. But this is a spin coherent state, sorry. That's this thing here. And the spin squeezed state, in analogy with bosonic squeezing, is something that has one variance below the threshold, let's say, of equal variances, and the other one is above it. And in fact, in certain limit, you can think of this as a, let's say, if the spin n goes to infinity, then the x and y directions, they become actually bosonic x and p operators, so to speak. So that's more or less the analogy. And the application of this state is that actually it can be used to detect magnetic fields, for example, to detect phases. And that's the original motivation for introducing them as well. And the idea is that instead of a spin coherent state in, let's say, this collective block sphere, you would have a state which has one variance which is slightly squeezed. So this area here are the two variances in orthogonal to the mean spin direction. And so when you rotate it, somehow this is more sensitive to rotation with respect to this. This is intuitively more or less what's happening, and that's the references in which this paper was introduced by Wien, essentially, and Kitagawa, Ueda, and Sorensen and others. So actually Sorensen and these other authors, Duan, Chirac, and Soler, they actually noted that this state, well, it was noted right away that such a state as an n particle state should be entangled, but quantitatively these people show that this is actually the definition of the spin squeezing parameter gives also an entanglement weakness. So if you have this combination of quantities below the threshold 0, then your state must be entangled. So the same definition of a spin squeeze state coincides with the necessarily entangled state. And then all of this was generalized in many ways. Maybe I don't go into all of these details, but let's say that Gesatot and others, with my former PhD supervisor, had already derived a full set of inequalities similar to the original spin squeezing inequality. So you get, let's say, a whole set of them, that if you measure these three variances in the orthogonal directions, you can tell whether if your point given by your measurement is inside this polytope, you don't know, but if it's outside, the state is definitely entangled. And since this is a closed polytope, there is no additional inequality you might think of which would improve over this. So you need only to check this set of 4 of them. And either the state is detected or you should measure something else. That's more or less the idea. And okay, this is just a panorama of many possible states you can detect with this. And all of them are sort of generalization of the original spin squeeze state and can be used especially for meteorological applications, but also in general for quantum technologies. So now, first experimental results I would like to show is actually the latest one in which I participated. And this was an experiment in Hanover where they have a rubidium Bose-Einstein condensate, and essentially they put it in a level in which there is 0, 1, minus 1 spin, and all particles initially are in 0 here, and then they collide and they go into a higher spatial mode, and but then in the plus 1 and minus 1, this is called spin exchanging collision or something like this. And so all the 0 collide and go in plus 1, minus 1 in an entangled state. And essentially you get at the end of the process a many-body entangled state between 2 spatially separated regions. And now they wanted to prove that such a state is entangled, and they don't have, let's say, so much noise that it kills the entanglement somehow. And so we developed this criterion that, well, in this case it was very well suited for what they measured, and but this I think is not an essential point here. And the only thing is that, again, this is this threshold is valid for all separable states. If you go below it, the state is entangled, and in this here graphic you can see that the experimental points are the green ones, and they went below the threshold, which is also the threshold is given by experimental data, which is the orange one. So they verified entanglement up to certain, say, confidence. Okay, so this is also showing that this is what the quantities that they measure. So that's the only thing. Okay, this slide I may just jump. Just wanted to tell that there are very many theoretical works, especially on this topic, and you can think of many possible generalization of this approach, and most probably there is a paper in which this generalization is treated in some way or another. And okay, so now other question arises, apart from distinguish a state whether it's entangled or not, is whether how much it is entangled, so to speak. So, okay, first, let's say heuristic way to define quantify entanglement would be to say to have a many-body system and let's say dividing it into, so let's say distinguishing how many particles are in each entangled set. So more, in other words, you define such a state which is still a product state, but now the units are not single particle states, but are many particle states, let's say. And depending on how many particles there are on the highest, so which is the highest number of particles in the units, you call the state K producible. So if in this case, for example, the state is 4 producible because you need at least one of the states here made by 4 particles. And the concept of entanglement depth is something which is K plus, so it has a depth K plus 1 if it is K plus 1 producible but not K producible. It's like a hierarchy now of things. And so this is one way to quantify entanglement, and you can pretty much with the same reasoning you can define now, instead of only one threshold, you have many thresholds depending on the depth of entanglement. And other than that, the reasoning is the same. And you can measure your collective variances, you get a point, and you get some standard deviations and so on, and then you can tell in your confidence region what is the depth of entanglement. And in this case, this was again in Carsten-Clem group, an experiment in which the point is at something like 68, and within 2 standard deviations it goes to 28. Okay. And maybe I don't give much more details here. And the same thing, well, here it's a different experiment in which now the entanglement is created by atom-light interaction. So there is a measurement which is called quantum non-demolition measurement that during the measurement process and here is more or less visualized, you create entanglement in the atomic ensemble, and the depth of entanglement somehow increases up to a certain point, and when you interact too much, you start to have noise, scattering between particles and so on, and then you lose entanglement. At least you don't see it anymore. Yes, so this was one way, and the other way is more like an operational framework, which is based on what is called an entanglement monotone, which is more or less similar to what Laura was talking about before. So it's a general resource theory in which now the operations are local operations that you can do on each particle, plus classical communication. This is called local operation and classical communication paradigm. And so your measure of entanglement should be something which, at least on average, should not increase under local operation and classical communication. And then, well, it should be 0 separable states and so on. And in this way, you will define many entanglement monotones, which turn out to be non-equivalent to each other. And so it's a very complicated theory. But it doesn't really matter for this talk. What I want to tell is that there are some monotones which you can define based as optimization of a set of witnesses. So here you have a set of witnesses and plus minus, and you define a monotone as maximum between 0 and the opposite of, let's say, how much you violate that witness. And so this is an entanglement monotone. Actually, for each m there is a different entanglement monotone. And the two of them coincide with something independently defined as here best separable approximation and generalized robustness. So these are monotones defined up from a decomposition of a state. Loosely speaking, let's say how much noise you can add to your state until it, for example, becomes separable in this case. Yeah. This is the sort of robustness, as the name suggests, of your state under noise. And so this is quite a meaningful measure for, at least in many-body physics, I would say. And what we did was to prove that when you violate, almost last slide, when you violate this criteria, you can tell also quantitatively what a lower bound to this thing. Maybe I skipped the technical details. I jumped right away here, in which you can, based on the same, this is spin squeezing parameter. You measure this. Not only you can tell the state is entangled or not, you can give a lower bound to these two measures here. And this is again experimental points. And let's say, so I mean, you can give a number from which has the meaning as a sort of a robustness measure. And yeah, I think that's it. That's a similar experimental data from another experiment. And so maybe I just thank you for your attention.
Question.
I kind of missed the second last experiment that you showed, and the one before that. Yes, this one.
Yes.
In this setup, like, what happens at large times?
So essentially, the thing is that they have an atomic ensemble, I mean, that's a very typical experiment. Many experimentalists use this, let's say, approach. And it's broke by light, and then they detect the light afterwards. And this way they can tell what is the spin of the atoms. But by this interaction, they also entangle the atom, right? So this is what happens. But not only they entangle the atom, there is also some noise because there is some scattering between the light and the atoms. So you get some atoms kicked out, for example, of the ensemble. This is one effect. So the thing is that now if you probe it for relatively moderate times, you are just mostly entangling the atoms, and you don't lose many of them, let's say. But if you keep going, then at some point you just lose all of the atoms and you don't have any more entanglement or anything. So somehow this is what happens here as well. For some, actually here is more than time, so it does not look as time. The x-axis here is number of photons, but more or less the idea is similar. And in fact, this quantifies times in their experiment. But you can think of it also if you push more photons, then you have the same effect. But just they don't put the photons all together. They have one pulse and so one laser, and over time the number of photons increases as well.
Thanks.
More questions? I actually had one, it's okay if you when you had the witness for the depth of entanglement, it means that at least you need so many particles that are entangled, right?
Yes.
But is there a way of, let's say, discriminating what kind of entanglement, if it is genuine entanglement between those particles? Or
no, actually it's a sort of a complementary. So another way, which I didn't mention, but another way of distinguishing in the multipartite case entanglement would be to say it's entanglement between a certain bipartition, or if I divide the system in two parts, however I take the two parts, it's always, I don't know, looks separable, but then you can have, no sorry, the other way around. So it's entangled with respect to what also bipartition or not. But I mean, this is sort of a complementary approach. You cannot tell, so it would be, for example, separable if you take certain bipartition, but nevertheless, within this bipartition, there is a group of, I don't know, k particles which are entangled with each other.
Okay.
So only for certain cuts you get entanglement, but there are other bipartitions, for example, in which the state is separable. Yeah, I'm not sure if I confused things or clarified.
No, I think
Just a quick question. I was just a bit struck by terminology. I mean, we always talk of separability at the level of pure states, and here you're talking about separability at the level of density matrices. Yes. And I just wonder, is it just a casual accident, or are there really quite fundamental?
I mean, I imagine that
I can see some already, but
I'm not sure we use the same terminology, but separable state also in the pure state case would be a product state, right? Tensor product between two things. So this notion generalizes this for mixed states, because in the experiment actually you cannot assume that your state is pure, otherwise it would be somewhat trivial to...
It's a question about the terminology and why you're using the same.
Well, it's a terminology, I think it's just the same, just that generalizes to density matrices now. So separable density matrix you might call it if you want, but...
Well, can I put a slightly different aspect to this question? I mean, what about, as it were, trivially entangled states, just through symmetrization or anti-symmetrization?
Yes.
Now, would you call those separable, and would those correspond
to those I would call it entangled, but it depends. So let's say, depends how do you define the subsystem. Let's put it this way. So if I tell you I have n particles, and these n particles are bosons, or for example, let's say two particles, right? So if they are bosons and therefore they must be in a symmetric state. Okay, depends. If you assume that this particle can be distinguished by, let's say, they are in two different lattice points, then the definitions coincide. But nevertheless, I'm just saying, if you have two bosons and you tell me I have two particles, and I would like to define entanglement between these two particles, then a bosonic state is entangled.
Right, but are you familiar with the literature I'm talking about? This is a literature in foundations in accordance with which entanglement achieved purely through symmetrization or anti-symmetrization is trivial.
I think I know some literature you are talking about.
Right, so that should it not?
I think it's a slightly different concept in that. So if you would consider bosonic entanglement trivial, then it's a different concept. Because actually, the way they obtain entanglement in the lab is exactly because the state is bosonic. Just because it's bosonic, then they get the entanglement essentially. But the thing is that it's still, first of all, useful, a useful resource, and secondly, it's also meaningful in the sense that you are not, so if you will be forbidden to detect the particles, then I would agree with the, let's say, I could discuss what is the meaning of entanglement or not, but in this case, it's actually, so you see the spots on the camera, and these spots are the different particles which you then associate with subsystems. So then it's a meaningful question to ask, was the state of these particles entangled or not? So, in other words, you have a bosonic state in the beginning, but then when you detect it, you sort of define your subsystems by the spatial position, and you sort of, I don't know. So in this case, you reveal the entanglement somehow. I'm not sure if we have time for more.
I mean,
exactly to answer.
You said that that you consider mixed states because they're more realistic.
Mm-hmm.
Now, what you can have is that the mixed state shows no entanglement, but when you purify it, then you find that there was entanglement, and that then shows in the mixed state as discord. Have you considered that?
Not really, to be honest. So I am aware of this, let's say, theory in general, but no, we didn't go into this problem, so I'm not sure.
I can show you some references then.
Okay, yes, it would be interesting to, if you have some points to think about.
I think this is super relevant because it's a generalized sort of measurement. The photon is not recording the microphone.
yeah.
Can you give us the reference?
It's about the Discord. Is this related to that comment?
Well, like maybe let me just ask.
We finished.
Very quick question. Can you compute what happens with the photons and then in your plot recover back the entanglement? I guess not, right?
What do you mean?
Like, because this is a sort of generalized measurement in which at the end the photon is not accessible to us anymore.
Yes.
So then this plot that you showed us with the entanglement, this is for a generalized measurement of just the system. So then my question is that is there any way that from your experiment with the photon signals, can you recompute it backwards and get back the entangled structure again?
No, I don't think so. So the thing is that physically you lose the particles. So I think it's just something in which your state is not anymore the same. I mean, it's just really there is no entanglement anymore there, I would say. So actually there is even less particles. It's a very strong noise effect. It's not that it's a detection problem that you don't see the entanglement. It's really that your state gets like destroyed.
Can you retrodict?
Yeah.
Can you retrodict is the question.
Yeah.
Yes, but I don't know. I mean, to me it looks something, it's like, I don't know. Maybe there is something I missed, but I would say that simply it's not a problem of the photons themselves, it's also the atoms. So you lose the atoms themselves. It's not that, so from the measurement you cannot tell the atom where it went. So, and I don't know what's being said. It's just like it got lost. I don't know. I mean, maybe it's something I missed, but I think it's just that it's really you destroy the system. Also, I mean, you not only detect it, but you also destroy it a bit.
So with this, we finish the session, the last session of today. So let's thank Giuseppe and all the speakers again.